Okay, let's go back to the MITRE attack, okay, framework. Okay, I've introduced the reconnaissance, okay, this tactic, okay. Of course, there are certain other tactics which is important, but among them there are about more than hundreds of techniques, and of course for for students or for general people that does not does not major in cybersecurity, they may not know what exactly which they may not know exactly what is the definition of each techniques and what, for example, if I collect malware, if I collect the behavior of a malware, I draw the figure like blaster. Okay, it is. I think it is a little bit difficult to partition those behavior into different stages, and you can label different stages by using the techniques and tactics used right here. I believe it is a very difficult task to do for even for a security expert. So I would like to use the MITRE tech as an example to introduce our next topic. Okay, so our next topic should be language model. Okay, language model. So here most of the time I use the Google's introduction to those language model, but I found two very useful resources for you, which talks about what is word embedding. Okay, and unfortunately, one of them is English and the other is Chinese. So, but the content is exactly the same. Okay, exactly the same. So, if possible, okay, you can try to take a look at these articles. Okay, it explained the word embedding this concept quite well. Okay, the Chinese part is exactly the same. Okay, they use the same content to explain the word embedding. Okay, so let's take a look at the first articles, which is word embedding. Okay, this one. Okay, so basically, as we mentioned before in previous class, okay, when we talk about how to deal with sequence data, right? Sequence data has different types of sequence. Okay, for example, it's simply just a sequence. Okay, ABC. Okay, it is a sequence, but we mentioned it before. It is not quite useful to use a neural network. Okay, if you do not do any pre-processing. Okay, so let's take a look at my let's take a look at this one. Okay, so we mentioned it before, but I would like to revisit it. Okay, so if you have a data and it is a sequence, so maybe your data looks like this one. Like this one. Okay, and we talked about it before. Okay, that is your first data, right? That is your first data. But how did you transform your data, especially text-based? Okay, especially text-based data to a table, because we always use this table to explain different algorithms, right? So how did you transform your text-based data to a numeric data? Okay, we mentioned it before. We have two very awful, okay, not useful approaches. Okay, one is the index, right? 1, 2, 3. What does that mean? What is that? That means, okay, the first, okay, maybe we use another word. Okay, we use another word. POS. POS stands for position. Okay, if I like to transfer text-based the sequence data to a table, okay, you can say, okay, the position number 1 is A. Okay, maybe I can encode A by using a number, right? For example, A is 1, B is 2, C is 3, D is 4, A is 1, C is 3, B is 2, something like that. So that I can simply just encode the original text-based sequence to a numeric data. So I simply just write 1, 1, something like that. If I have another sequence, which is also composed by A, B, C, D, I can use the same way. However, there are some, but sequence data is not always that simple. For example, if I have a data, okay, the sequence data you collect, because it is sequence data, all right? So you have to spend some time to observe what event or what item has been observed by your monitor. So you know, okay, the first one is A, and then you wait, okay, the second one is A, the third one is B, C, D, F, G, something like that. But always, okay, if I have a monitor to observe different event, okay, event-based data, there's always some noises. For example, if you have a sequence, okay, and there's a noises right here, that is F, right? That's F. And originally, okay, D is the fifth event you observed. A is the sixth event you observed. But if you observe certain noises, or if some noises just happen, some event just happen between D and A, means that it's F. So all the rest of the event will have to shift one position. So the F will be the sixth one, A will be the seventh one, C will be the sixth one. And as we know, if we design a neural network, right? Position 1, position 2, position 3 as the input, okay? And we do some neural networks right here, okay? No matter what kind of Y we like to do. You know, if there is a noise or there is an event which is in somewhere that you don't want it being observed, okay? Because the neural network, the input neural network, is sensitive to the input index, right? So all the rest of the A, C, B, C, A will shift to next neuron. So maybe that is not what we want. So we mentioned it before. So such kind of encoding approach, okay, use the position. Okay, if the position is not fixed, if there's some possible event may change your position, may shift your position, may rotate your position, something like that, you should not use such kind of encoding. OK， 中文再说一次哦。如果你的序列资料它是有顺序性的，而且它的顺序性跟它的位置是很有关系的，所以有可能你在观察你的事件的时候，比如说你多了一个 F 在 D 跟 A 中间，那这样 A 就必须往后移一格。那你这样子，这个新的 noise 跑进来之后，那因为 neuron 在接收那个 P 的时候啊，它其实对位置是敏感的，对吧 ？input 的第6个跟第5个就是不一样了。你要知道，在原本的 neural network 里面，其实原本的每一个 column 啊，比如说你的身高、你的体重、你的薪水，它们应该都是 independent variable 嘛。所以你的输入就是跟说，哦，这是 weight， 所以它是对应到 neuron 1啊，这个是体重啊，这是身高，就对应到 neuron 3这样子。可是如果你用位置来定义 neuron 的话，它会非常的危险啊，就不适合这样子做啊。这个我们之前已经讨论过。So that is not quite feasible to encode sequence data by using its position and use this position as the input of your neural network. That is not quite feasible. Okay, so the next things we talk about is the next approach we talk about is, okay, maybe I can draw a new one. Okay, the next approach we talk about is Unground and one hot. I think we talked about before. Okay, so basically you still create a table like that. However, the features you use is not the position. It's not the position, right? The feature you use is exactly what kind of event you can observe in your system. So for example, that is A, B, C, and D. Okay, there are several different ways to fill in this table. Okay, for example, you can use count. Frequency count, right? In this sequence, okay, we can see that there are 4 A's. So we write 4 right here. There are 2 B's, right? 2 C and 2 D. So that's how we describe this sequence. However, you know that we mentioned it before. The relation between different events you observed, especially the ordered relationship, disappear. Right? We simply just count how many times you observe this event in the entire sequence. So if possible, okay, if possible, there's another way that okay. You want to keep its neighbor relationship. So basically you can try to find out how many different neighbors relation in this entire database, in their entire dataset. For example, we have AA, we have AB, we have BC, CD, DA, BD, DC, CA, right? And you can keep just working on it. Okay, how many AA in sequence number 1? 1. How many AB? We can see that there are 2 ABs right here. How many BC? I believe that something like that. Yeah, I think that. So you can use Unground features and try to figure out how do you present a text-based sequence data by using numeric table. And of course you can use one hot. One hot simply just means, okay, if the count right here is not 0, you can simply just use 1. 1 means this observation exists in the original sequence data. Okay, so you can for example, we can find another one. A B, D, C, right? So if you count it in this way, AA, AB, BC 0, BD 0, DA 0, BD, DC, CA, something like that. Okay. Okay. And still, it is. We believe it is not. It is. Oh, of course, it is much better than simply just count how many items in your sequence. It is a little bit better, but however, sometimes we don't think it is good enough. So next thing is, if we have multiple, if I have a sequence, okay, it has many different items, and I would like to convert, we say transform, okay, transform from text-based data into numeric data. Is there any better way? So especially from the perspective of using the neural network technique, yes. So I think the first things we might talk about is word embeddings. Okay, so that means the sequence we talk about right here is English words, right? We have many different English words. They are viewed as tokens, right? Events, and in a sentence, there are several different words, right? We combine words into sentence, and there are several sentences. We combine different sentences into paragraphs. So that's still sequence data, right? And the event is the words. So basically, if we would try to deal with the data which is words, sentence data, of course you can use the Unground ways. You can use the count ways to describe a paragraph by using the word count, by using the Unground word count, but it is not that efficient. So we'll have to introduce how do we use a neural network to represent a word, a sentence, or even a paragraph. Okay, so this tutorial is provided by Google, right? So you can take a look at this link. Okay, it shows a trend model. Okay, of course by Google. So every dot right here is a word. Is a word. Okay, of course this word should be in a very high dimensional length space. Okay, and we can see that there are different relation between each dot. And right here, can you see the left hand side? Because it is a very high dimension length space, so it draws the these words. Okay, these words, 10K words. Okay, by using PCA. So it has dimension reduction to into two or three. Use three dimension to represent the relationship between words, and those words are already embedded by using the word to vector, which is a technique used by these these pages. Okay, so that we can see that what exactly the output. So basically, you can view it as a model. So you input a word to this model, and this model will output a very high dimensional data space. And this data space will be all numeric data, and this data represent this input word. So what exactly this relationship does? Okay, so maybe we can see just two dimension, okay, by using PCA. So let's simply just select two words very close to each other. If you take a look at this value, okay, maybe you can see this one. It says originally this data space is quite high, right? It's quite big, but we use PCA to map it into a 2D surface, and this 2D surface only describe 6.3% of variance, and I believe you know what it exactly means. It is a very low variance, right? If we use 3 dimension, it only describes 8.5% variance. So that means this 2D, okay, this 2D this 2D projection is not quite well. So let's try another kind of dimension reduction. Let's try to see if we can find some relationship between different points. So that is, and okay, let's try to have this moving. Okay, that's okay. We can stop. We can pause it anytime right here. Okay, so we can see that it's a 3D. it is a 3D projection. Okay, so maybe we can I don't know, select two of them. I think that is a good example, right? In this example, okay, you can see that this dot stands for AID add, right? This, which means help, right? And that is assist, which also means help, right? So basically, those models, they are trying to do something that if originally their semantic meaning of the input words is similar, and then after we do such kind of model, this model is called word-to-vec. After we do such kind of word-to-vec model, the model will output sorry the model will output a high dimensional numeric vector, and if the semantic meaning of the original word is similar, then the output numeric vectors in the latent space should be close to the word which has similar semantic meanings. That is this model trying to do. Okay, you can try it by yourself. Okay, but as I mentioned before, because it is only a 3D. I mean, it is just a projection. So sometimes the variance is not quite clear. So sometimes even if 2 points they overlap with each other, but maybe because in this 3D dimension space they are overlapped to each other, but in the original latent space, which is a very high dimension, they are far away. But we have only 3D. we have only 3D projection to observe those data points. So maybe sometimes they do not have similar semantic meanings. Okay, but theoretically, in the high dimensional latent space, closed data point will have the similar closed data point in the latent space will have the similar semantic meanings in the original word space. Okay, try to play with this figure. Okay, yeah, sometimes you can find a very interesting things right here. Okay, so we're trying to do such kind of a model, try to convert word to numeric data. So that is called word embedding. So we like to represent text as numbers. So sometimes we use this word called vectorized. Okay, so I think we mentioned it before, right? We have a one-hot encoding approach. So you can build up your own dictionary. So you have a document, you have several documents, and you simply just count how many different words has been used in those documents. For example, you have 1,000 words. So you can create a vector with 1,000 dimension, and each dimension specify, okay, this word. For example, it has 5 different words in its dictionary. So this word, the, okay, it represents as 00001. So it's very simple, straightforward one-hot encoding. But that is not good enough, because for this one-hot encoding, basically the dimension of the vector you use is exactly the same how many vocabulary in your dictionary, right? So it's right here. The vector with the length equal to the size of your vocabulary. So if you have 1,000 words or 10,000, even 100,000 words, your vector will be very large. It is very inconvenient to do the further, for example, a classification or a clustering. So usually that is the basic, but we don't use it in this way, right? So you encode each word with a unique number. For example, I can use 5 to represent the, use 0 to represent cat, use 1, 2, 3, 4, 5. Okay, use 5 to represent the. Use 1 to represent cat. Use 4 to represent SAT, set. But still, as we mentioned before, after we have such kind of encoding, we will have to apply different machine learning or neural network algorithms. Those algorithms are basically what? Add, abstract, subtract, right? Times, or some nonlinear relationship, right? We have different mathematical tools to formulate different machine learning algorithms. But basically, if they use add, what exactly is 1 add 1, right? 1 add 5, that is 6, right? Cat is 1, the is 5. But if we have some other machine learning algorithm, they do add. But what exactly means add? A cat add to the. It is a little bit not make sense, right? So basically, we would like to use even more better ways to represent text. Okay. So word embedding will give us an efficient, dense representation. Dense representation means if I have 1,000 word, 10,000 word, or 100,000 words, I don't have to create a vector which has 1,000 dimension, 10,000 dimension, 100,000 dimension. So we would like to have a dense representation. Okay, so that is the important things. Similar words have similar encoding in the latent space. So maybe we have such kind of 4-dimensional embedding, such like this. Cat represent as 4 numeric numbers, 1.2 minus 0.1, something like that. But however, how do we create such kind of embedding matrix so that we know cat equals to this specific embedding? Okay, so here, of course, Google provide some example code right here, so that you can download a dataset from IMDb. IMDb is a movie comment database, so we have a lot of different words used in these comments, right? So, however, in this document, it only tells you. Let me see where it is. Okay, right here, just simply right here. Because Keras TensorFlow already deal with all the other things. So for the perspective of using it, you simply just create a new layer in front of your neural network, or in front of all the other machine learning or neural network algorithms. Okay, the only thing you have to do is to create a new embedding layer and prepare the documents, the words you would like to use. So this embedding layer will automatically create such kind of right here, such kind of embedding for all of your words used in your training data. So so I think we should take a look at this one. Okay, so the 1005 means embed a 1,000 word vocabulary into 5 dimensions. That is simple, very, very simple. The only thing you have to do is this. Okay, everything you have to do is this. So here's an example that you can simply just put. Of course, there are some preparatory things you have to do. If your data is not clean, for example, you collect your data from a web page, you collect your data from some text-based database. Okay, we will talk about how to what is the theory behind this embedding layer. But actually, if you really only need to use it, okay, you can simply just use one line right here. It will deal with all the other things. Okay, so you have a 1,000 word vocabulary. So basically, it will count how many words in your training data. If your training data is more than 1,000 words, we will try to remove words which has which it will try to pick top 1,000 words which is used more frequently and discard all the other words, because those words are observed more often, right, in your document. Okay, so you have to define your dimension. You have to decide how many words you would like to use in your dictionary. So that is, and after that, okay, so you can create whatever model you like. So that is a sequential model, right? That's a sequential model. So for example, you have a polling layer, you have a dense layer, you have a dense layer right here. But before that, you can use embedding layer. Okay, and in this example, we have the vocabulary. I don't know what exactly the right here, 1,000 vocabulary, 10,000 vocabulary size, and each vocabulary was embedded into 16 dimension. And the 16 dimension result will be fitted into a polling layer, and then a dense layer and dense layer. And I believe this example is a classification example, so it has only one output value, which is either 1 or 0. Okay, basically I think this example is about movie comment, right? It's about movie comment. So it is a classification problem. You input a lot of comments, okay, as your training data, and the target is this comment positive or negative, right? Because the database will specify it is a positive comment or it is a negative comment. So basically, when you input some other testing text, your model, which is right here, right? Your model is right here. First, it will try to embed your text, which is your comment, your new comment, and then do polling, do dense, and the last output value will be close to 0 or 1, which represent it is a positive comment or it is a negative comment. So if you're interested, please just copy the code right here, okay, and try to feel how it works. Okay, so that is embedding. If you simply just want to use them, you simply just use this very simple one. Okay, however, in our class we not just simply just use this one. So I think I can stop right here, so that we can explain it more in an integrated way. So it is 10:50 right now, so please come back at 11. Okay, we take a 10-minute break. Please come back at 5/11. Okay, we take a 10-minute break so that we can draw some figures. Okay.